Well, thank you, everyone, for coming. Thanks to the SIG and Miles for organizing, and Elance for hosting us tonight. So I'm Ron Bodkin. I'm the founder and CEO of Think Big Analytics. Think Big, we're a purpose-built professional services firm for big data. We started the company 3 years ago with an exclusive focus on helping companies get measurable value from data science and data engineering around big data. And what I'm going to be talking to you about today is some of what we've learned and seen in our experiences in terms of how can companies really make big data come alive, especially around the exciting trend of the Internet of Things. Machines, devices, sensors. This is an area that we ultimately think is going to be the most important area for big data, where the growth trends are clear that more than any other data source, machine-generated data is growing faster and will become dominant over the next few years. Today, consumer-generated, click streams on mobile and web are the largest data set around, but in fact, machine data will dwarf that. So I'm going to talk a little bit about some of the general context, what's going on, talk about some of the trends around that specific use case. Then I'll delve into the architecture, some of the different technologies that come together, what I think of as big data, some of the new and novel techniques that are happening, and then talk a little bit about methodology and skills and work needed in order to be successful. Definitely, though, I want this to be a conversation, so I want to leave a little bit of time at the end for Q&A, for your questions, your interests. Just out of curiosity, who here is by training a mathematician? All right. Who here is by training a computer scientist, computer engineer? All right. And who here doesn't like raising their hand? So who's more on the business side rather than on the technical side? All right. So we've got a fairly even mix of folks. I would say that one of the things that we firmly believe is that big data is indeed a big change. What is big data? I think you must define your terms. The term is now trendy, and so if you look, lots of people are calling lots of things big data that I don't think of as big data. So it's worth defining. What do I mean exactly? Well, to me, fundamentally, big data is around a revolutionary new set of technologies that are based in open source, that are allowing you to do things with data that weren't possible before with a legacy database and analytic architectures. So it was created and flourished right here in Silicon Valley in organizations that were pioneers. Google certainly took a lot of specific ideas and generalized them, creating a foundation, and then open source communities formed around technologies like Hadoop and Cassandra and HBase and Storm and others to build more generally shared and usable implementations of these. But fundamentally, big data is, in our view, it's about these new techniques of working with data in a more flexible way, based on commodity hardware that can scale out, that let you solve problems in ways that you really couldn't before, because you can address the volume, variety, and velocity characteristics of the data, and ultimately let you create value out of that data, right? So fundamentally, to us, it's about modernizing the way computers work with data, right? I mean, we've basically been stuck with a 1980s way of thinking about data for a long time. And I don't know if you noticed, but computers have gotten a lot more capable in the last 30 years, like 1,000,000 times more capable. So basing the way we store and process data on the designs from the 1980s really doesn't make a lot of sense. And that's why this field has such a powerful potential, because we've organized our way of working with data based on keeping really small samples, tiny amounts of data, eking tremendous amount of information out of a principle of let's store just the least amount of data and pre-analyze anything we want to answer and only touch data once, which all made sense in the 1980s and doesn't make any sense in today's world. So that's why we see across so many industries, and I'm still learning this control, why we see across, I guess there's no pointer, across so many industries, the applications coming about, and we're seeing, probably no surprise, the first applications in business to consumer. But now, with Internet of Things, we're seeing a lot of activity, a lot of interest around business to business use for big data. So, next slide. And indeed, the first applications of big data were in some of the web scale pioneers. Prior to starting Think Big, I was actually VP of engineering of a company called QuantCast that was one of these pioneers. At QuantCast, we first rolled out audience measurement, so directly measuring every page view, every ad seen on the internet, where traditionally people had a non-big data view of using small samples and panels to measure the internet. And we said, well, Nielsen and Comscore are wrong. You can directly measure the internet and use data science inference to statistically correct to understand the kind of demographics and interests of people, and went on to roll out a revenue-producing product called Lookalikes that has become the basis of over $100 million a year business at QuantCast in the fast-growing real-time bidding advertising market. And that's a microcosm. The same sort of things happened at Google and Twitter and LinkedIn and Facebook, where you saw the use of big data techniques allowing them to innovate and create lots of value around the data that they had at the core of their businesses. And then as a follow-up to that trend, what we've seen happen is there's now been an explosion of innovation overall in the industry, where you've got lots of, the first wave of investment in big data was companies that contributed to open source. The second wave of investment has been around investment by first venture-backed startups building products, platforms, and tools, and then subsequently the investment by larger systems companies in investing and integrating their technologies. So we've had a lot of investment. We've certainly had, though, as a result of that, a fair bit of confusion. So a lot of people we see are out there not really understanding, well, what things are big data, what things are being positioned as big data, but maybe are more of a legacy technology. What are the ways these things work together, and understanding how to put together solutions to get results. So what we're going to talk about today is a little bit more detail around how some of these new technologies come together and what they can do. So one thing I think is important is we've seen in companies that have followed through and adopted big data, a series of stages of adoption. That this is not a big bang transformation. One day you're an organization that's working with legacy BI, and the next day you're innovating and reinventing your industry based on being a data-driven organization, right? It takes time. There's a series of steps that happen. And most of these steps here have been witnessed only in Silicon Valley and some of the pioneer companies like the QuantCasts and Googles and Facebooks of the world that have been investing for the last 5+ years in these technologies. But what we see is enterprises are following some of the same footsteps, where moving beyond traditional approaches to working with data and then analyzing that data, you start saying, a first move will be containing costs and scaling, starting to put more data together in a single place. Often you'll see business cases around just reducing IT costs. Not very interesting from a data mining perspective, but certainly often a first move. The next place where things start to really get interesting is a shift to more agile analytics and insights. Starting to say, we're going to rely more on capable analysts, capable data scientists to work with data in a more complex and raw format to extract meaning and answer questions, instead of the traditional analytics approach of let's pre-organize the data based on questions that we know we're going to answer and make it very time-consuming to answer new questions. Right? So putting data in a raw format together in a common place where you can apply analytic techniques and structure the data enough for your problem is really a big revolution in how we think about looking at data and organizing it. And in a way that you finally have democratic access to data. So often what we found is even where there was an ability to store data in a traditional MPP database, there was insufficient funds to really allow people to have access and play in that environment. And so you didn't have practical access. Going beyond that, you start to really get into interesting spaces where you're leveraging predictive analytics and more automating business decisions, right? So once you've built insights, instead of setting up a system to do more and more manual analysis and encoding of rules, we see a lot of opportunity around innovating current business, optimizing, automating decisions. That could be in the advertising arena. That could be deciding on what ads to show based on algorithms that are doing machine learning instead of humans curating serving rules. And as we'll see, there's lots of opportunities for that in the Internet of Things space. We'll talk about that in a little bit. And then finally, organizational transformation. Really starting to use the power of data and data science to create new products, new features, start to sell data and analytics as a higher value to core customers, extending your existing offering portfolios. So this is where we see big data going in a series of stages of adoption. And we also think that this model is something that can be applied within a company, right? So that it's great to have a lead team, a first group that's running ahead and doing more advanced things and showing the way to colleagues. So in a larger organization, you have that opportunity to lead the way and to really show that kind of value. Now stepping into more of the Internet of Things and the space of connected products, we really see that we are entering a new world of smart connected products. We've got so much more network connectivity, more standards around internet access, which is driving a world of connectivity. We've got the ability to embed sensors in all kinds of devices and products. We are putting software into all kinds of things that we didn't have before, that whether you're looking at devices like a Fitbit for personal information, whether you're looking at a supply chain application, RFID devices, a factory, whether you're looking at supporting devices in an IT server farm. There's this range of products, and they all have a lot of these characteristics that they're able to sense information. We have software that's powering these devices. They're configured and connected in interesting ways, and they're on a network so that it's feasible to collect data about them. Those characteristics are very interesting. With that capability becomes first order, there's been a lot of investment in Internet of Things around just plumbing, collecting data, and that's important, right? You have to be able to collect data. But beyond that, the really interesting thing is, well, what do you do with that data, right? I mean, it's this night and day difference of previously, organizations have mostly been flying blind with very limited information about what are people really doing with the devices that they've got out there, right? We don't know. We speculate. We do surveys. We sample. We look at broken things and try to figure out what's going on. Suddenly, you can directly measure, and it opens up a new world. So it's a pretty exciting time. And the other thing that's interesting about it is, with the ability to analyze and create value, you have a positive feedback loop that there's now a strong incentive to instrument and measure more, right? That suddenly, as you see value from taking connected products and looking at them, you have more reason to learn more, to capture more, to send more home. So you get a virtuous cycle of capturing more data to create more value and then analyzing it to further improve the business. Yes?
Okay, question. So who drives the standards to allow these devices to communicate together?
So certainly, in terms of how do you drive standards to have devices connect and communicate, that remains a bit nascent. There are a couple of standards that we've seen out there in different kinds of devices, but Internet of Things is so broad that different industries and different segments have very different standards, right? So you might have, I think it's IQTT, if I'm remembering the acronyms right, which is one more broad universal standard that's been put forward. You'll have standards around SCADA in manufacturing, right? So I think there's still a fair bit of balkanization that what application protocols run is still not well defined and not standardized, and I think that will take time to converge. But at least having a common transport layer and systems that have some level of flexibility onto how they can access and analyze the data will make big differences. But no doubt, the standardization of communication of devices is still very much underway and far from universal. So from a standpoint of what parts of an organization, so supposing your company is making a product of some form that's connected, that's a thing that might be on the Internet of Things. Who in your company might care about that? Well, the interesting thing is that the implications are broad across functional units, right? The general managers of business lines should care a great deal about how their products are being used. Those who are leading products, defining it, looking at features and pricing and so forth, should, again, have a lot of value out of looking at direct data around what's going on with those products. Those responsible for servicing devices, that's a space we've seen a lot of interest in driving better servicing of devices to serve the customer better and more efficiently. We'll talk more about that. Those in sales and marketing, needless to say, if you want to know how to sell and how to market your device, knowing what's going on, how it's being used, what's working and not is super important. And indeed, the whole supply chain, the engineering and manufacturing process is very much something where having access to data and understanding what's going on is important, right? I mean, if you have data to know what kinds of things are working and not, it can really impact your decisions around priorities of what you're going to invest in for future engineering. So from a business standpoint, some of the outcomes, some of the goals that we see around Internet of Things are in the improving service arena. You can see challenges like how do we better identify what things are driving costs of support? You know, what things are not clear or causing problems? Where are we spending money by reacting to fixing things that break rather than being proactive and servicing things before they break? How do we improve customer satisfaction by having a better service experience? How do we analyze churn to take a look at what kinds of customers are unhappy and are likely to stop using our product or service? You know, from a product management standpoint, there's all kinds of interesting problems like, you know, what capabilities do customers want? What places do we need to have better quality? What kinds of things are not being used and could be deprecated? You know, look into the supply chain, coordinating with component suppliers. You know, common characteristic can be certain kinds of components are unreliable or challenging, and being able to simply have access to the data to reliably know about that and respond in a timely way is important. Security is another important topic as we think about analyzing the use of devices and indeed responding to security threats. You know, as you think about business transformation, coming up with new offerings, one of the very common scenarios we see is those that own products are in a fantastic position to add more value to their customers by starting to up-level and offering data and analytics on top of the products. Benchmarking, understanding how others are using your products and, out there in the market, and to be able to guide on you're substandard in this area, and here's ways you might improve. That's tremendously valuable, and the people that manufacture whatever product or device it is are in a very natural position to be at the hub of that conversation. We've seen ambitions and interest in spanning from driving analytics and data around your own products to those of your competitors, although to date we haven't seen a lot of interest in customers providing that kind of competitive product data to a given vendor. But you know, if you had enough compelling value in an analytics service, that could be a future. And then sales, right? So being able to understand what customers are using, identifying capabilities that would be valuable to them, cross-selling, upselling, to predict before something is no longer usable, to say there's additional value to be had. Those are all interesting areas. So let's shift from some of these business outcomes to talk a little bit more about, you know, what are some of what's needed in order to deliver these, right? So one important notion is, well, what are the data sets that might come together? And one of the things that we think is really important about big data is that it's typical in a big data application that you're creating value because you're combining some new data set that has a characteristic that made it hard to work with in a traditional kind of technology with established high-value structured data. So we see it's typical that the kind of high-value applications in the big data space are blending complex data, large data sets, complex structure, less well-defined information with fast-changing information with more traditional structured databases, right? So some of the kinds of complex structured data sets that we see being important in the Internet of Things are sensors, time series of data readings from a sensor. That could be where something is located physically. It could be a temperature or a current. It could be a time series of capacity usage, right? Those are all examples of sensors that become important. The other thing that I think is often underlooked is, or overlooked, not underlooked, in this space is how much of the Internet of Things is around there's software on a lot of the things in the Internet of Things. Some of the things are virtual things. They're just software itself, right? So if you have a virtual machine, that's a thing that could be interesting, but it's not there's no physical manifestation of it, right? So the logs of software that talk about what it's doing, especially the alerts and warnings that it's encountering, are a rich source of information that become important to track as you're thinking about understanding what's going on. Likewise, understanding the configurations. You know, how are complex systems put together? What's connected to what pieces are coming together? As we all know, it's impossible to test all combinations of complex systems where you've got an exponential function of how many variants could be put together. So having information about configurations often tells us a lot around what sort of things are working well together or where there can be bad interactions that are unstable. Online activity, so shifting over to auxiliary data around what users who are having issues are doing, like interacting with a support portal or interacting directly with an online service. Text documents associated with those devices or items. Even in some cases, although we haven't seen as much of this, but the video, image, audio, kind of more complex, unstructured data sets that can be applied, right? If you have a video camera on a device, there's lots of information that could be analyzed. And indeed, social data, where cases where people are collaborating or interacting around devices, there can be useful information there, right? So those are all examples of some of these complex structured data sets, non-traditional, that don't fit well into traditional processing paradigms, that then get married to some of the structured data that has been out there that gives you a lot of context, right? So as you see something about a device, you do want to know who's the customer, when did they buy it, what's their overall geography, what's their size, what's their product bill of materials or catalog, something about the supply chain and manufacturing data, right? So we typically see combining data sets together to create systems that are providing a unique value to a specific company, that are high value and a little bit unique. So we don't think that Internet of Things analytics is an out-of-the-box, just pump your data in and magic comes out. It's a lot more around blending your data for your problems to create unique value for your business. And that makes sense because if you think about it, if you have a product, that product is core to your business. So understanding it, understanding how to make it better and how it work well for your customers is likewise core to your business. Yeah?
Just had a question. So you said that this is all multimodal data coming from different streams. So how do you annotate this for ground truth? And how do you normalize this? Because these will have different time scales, right? Mm-hmm. So what's the basis for kind of aggregating all this together when you're analyzing?
So I think one of the important things is rather than trying to place this into a single way of analyzing it, the big data approach would be to be able to land the data in a more raw format and not try to pre-anticipate a single way of representing it that puts everything together, right? So that gives you the flexibility to do different transformations downstream. If you wanted to put it together in a single way of representing it on a common time scale, you can, right? If you have a temporal analysis you want to do, but you don't want to throw out the raw source information that was higher fidelity, for example, right? Because there might be another analysis you're doing that's not temporal, where it didn't make sense to simplify the data in that way. So, I would certainly say that there's a range of techniques you can use, whether it be things like text mining on textual data, graph analysis on social data, that we see definitely time series methods being used, but also other forms of taking data sets and extracting features, right? Where you might not have a temporal analysis at all, but if you want to talk about what are stable configurations, you might have an analysis that has more to do with characteristics at a point in time to say, is this currently a stable configuration? So I guess I would say that one of the things I see is very powerful around big data techniques is you don't need to commit to a single representation. You have the ability to store data in a raw form, and then for your problem, you can test out different ways of representing the data and different algorithms to see what's creating value. Yeah.
Have you seen instances of temporal graph stores? Because I haven't personally seen anything.
So I would say I have not either seen anyone who's built a temporal graph store. I haven't run into that either. Right? So typically you'll see differences between graph analysis and temporal analysis. Although there's always things you can do, like you could put lots of time-oriented data in each node in a graph and do local analysis around time events. And kind of getting into what are some of the underlying technical capabilities to support some of these interesting needs, you again see the need to have a scalable infrastructure, right? To be able to store data in a raw format that scales, to have the ability to work at very different time scales, right? That on the right with predictive models, you tend to have a desire to do simulation and historical back testing on large data sets to be able to figure out what's going on, and then to be able to apply models very quickly, often in real time. If you're monitoring to say, is something unhealthy, is it likely to need to be remediated, you want to know that in near term to be able to respond, right? So you have that combination. We've seen in a lot of big data systems where you want to have a batch component to be able to train models, to be able to refine them over time, and a real-time component to be able to apply them very quickly and respond as events are occurring, right? So that can be detecting critical events, responding to them, providing near real-time graphs that not only have raw readings, but modeled outcomes in them, and also to be able to have the ability to do ad hoc analysis. In a lot of cases, there's a lot of power in being able to simply pull data together and have a quick view of what's going on and to explore and dig in and to test the hypothesis. Is this new problem we're running into caused by something new? These are complex, high-dimensional spaces, and so it's hard to anticipate what kinds of things might be causing a problem, but having tools that give you the flexibility to search and dig into those data sets are valuable. So those are just some of the technical capabilities that we see as especially relevant in this kind of IoT analysis. You know, as a bit of a visualization or a concept of how these things can come together, if you think about providing some kind of a visualization on top of this analysis, you might see the ability to have a customer have access to data, the ability to do things like search, right? A lot of times there's value in various forms of search to find things in logs, in data sets that are textual of various forms. The ability to proactively alert and alarm and prioritize. Many times what you see too is that systems have too many alerts and too many rules, so filtering down to the ones that are critical can be a very interesting problem. Combining data streams and visualizing them in useful ways, and being able to show in real time what's going on and highlight with visual capacity the ability to drill in, right? So a lot of this represents the work that comes out that might be exposed to a broader audience, where the data mining, the data scientists behind the scenes have done a lot of analysis and work to package things up and make things accessible to a larger audience. And indeed, analytics on device failures to understand what's going on and what's going wrong is certainly a powerful capability that can be represented there as well. So with that, maybe a couple of examples of real-world cases of customers we've worked with and some of what they're doing. So one case, working with a storage systems provider who creates IT devices and sells it out to many enterprises around the world, where they want to be able to store a lot of this kind of data around their devices deployed around the globe for their demanding customers. And they wanted to improve the way they pulled in this data and organized it, be able to do analysis across these massive data sets, be able to cost effectively scale the storage and processing of that data, and start to do predictive analytics, to do things like predicting when devices would fail, improve the customer satisfaction, or improve product planning. Right? And so there, we worked with them through a series of stages, from planning, understanding what was needed, through to doing a proof of concept and ultimately architecting an engineered solution to support that data science foundation. A lot of cases, what we saw was there was a challenge in terms of traditional database and storage technologies being used that couldn't handle the data volumes, didn't allow for the analysis, forced them to really keep small samples of data instead of working at full scale, facing basic scalability challenges in meeting their service, and making it very hard to integrate new data sets or respond to changes in the underlying product. As you started looking at advancing the product and adding more complexity, like clustered configuration or new software releases, each of those kinds of changes in the underlying data presented a significant challenge that could be remediated, improved quite a bit, with meaningful business benefits, as you see here, by really investing in a big data science approach. Yeah. So organizationally, that was championed by the service department. So you really had there, again, the people that were impacted were responsible on the business side, as part of the product group, were needing to address how do they serve customers better, how do they maintain great service while containing costs in the face of a rapidly growing tsunami of data coming in. Yes.
Why were they only retaining a small percent of the data? Was it a technical problem, or they just didn't realize that there was value in the data they were throwing away?
So they were able to, they had two pieces. They had a small amount of data that was online in an accessible format in a database because of cost and scalability constraints around the way they were operating the database. And then they had a large amount of data that was online in flat files that was incredibly hard to access, that it was a major project for people to pull specific data, literally mounting volumes and running grep across disk after disk. So it would take an engineer a week to investigate one thing if they needed to dig into raw data. Right? So it wasn't completely inaccessible, but it was so hard to access that it was a major problem. In fact, that's been a common theme, that one of the quick wins in big data is often ending what another of our customers calls the search parties, where engineers are out running down data sets off of USB keys and databases scattered across factories around the globe just to investigate a problem, where often it sounds funny, but boy, it's stressful when you have got a customer breathing down your neck about a problem and you're desperately trying to find the data to help you diagnose what's going wrong, right? So that's, in both cases, a common theme of people have just not had data at their fingertips and ability to process it in a useful way with legacy systems. Yeah.
Yeah, I don't see that changing. So I don't see, I think you're a service company, I just heard it. So I think that's part of the services that, is to find out what's worth it to search around. Because even like Amazon and others, not all data are online. That problem has not changed. Problem has not changed. I don't see it that changing.
Yeah, absolutely. We see, in these cases, what we've been able to do by putting data into Hadoop. You now have a much lower latency of access to data. You can build distributed search indexes that give you the ability to find data in a variety of ways. So it dramatically changes the economics and makes it a lot more feasible to access data in a raw form. So absolutely, I think the use of scalar architectures and open source big data techniques has dramatically shifted the ability to access data and to let you resolve issues.
How big was the data set?
So in this case, we're talking about a petabyte of data is the basic data volume, and continuing an exponential growth curve. And for one of the customers, and I have another customer, a similar nature, where it's maybe 10 petabytes of data. And then another example, again, a petabyte scale challenge around a network data provider, providing core network infrastructure, where you've got a requirement to process terabytes of data very quickly, be able to support security research to analyze emerging threats. Needless to say, that anything where you're doing analysis of emerging threats or behavior of bad guys is something where you can't stay, there's no fixed model that can work, right? As soon as you come up with a model to find the behavior, the adversary will react to try to escape your detection, right? So identifying patterns of those malicious actors and protecting the brand. Again, in this case, we worked with the customer through a series of stages, from understanding their architecture, analyzing what they're currently doing, validating some data science models, improving the ability to use big data techniques to identify threats in advance based on signatures before attacks were being launched. So, in this case, again, we saw that there was the capability of storing the data and analyzing it at scale was important, as well as the ability to do large-scale processing to validate and detect latent problems, as another example of being able to really analyze and create a lot of value around this Internet of Things, in this case, connected network data. Yeah.
Could you elaborate a bit more on the limited data retention challenge? When you didn't have the data, and if you need to collect those, and the costs associated with them, perhaps the resistance of collecting.
Sure. So elaborate on the resistance to collecting the data. In this case, we started working with a customer that had put together a Hadoop cluster, so they had some machines that had some amount of data, but they had limited amount of disk on each. And so they were in the unfortunate situation of needing to store very small amounts of historical data and throwing out most of the data. And most of the data was heavily summarized. So while it was being stored in Hadoop, it wasn't in fact following what you would think of as the best practices around how to use big data, where you would want to have larger storage and be able to look back at history. And in this case, in order to budget for petabyte scale implementation, you have to have enough of a business case that business is willing to make an investment in doing that. It's dramatically cheaper to do that with big data technologies like Hadoop than it is with a MPP database, but it's still not free, right? And you still need a business case. So, in this case, validating the ability to detect these patterns was important in building that case where the customer of ours has now built a competency center and invested in a next generation Hadoop architecture with much more capacity, not just to support this one case, but to enable a whole range of product value that they can create by using their data. Yeah.
You mentioned about the data. I don't quote me, but I believe I read that Facebook has a petabyte of new data every 3 days, so they have massive challenges in terms of data mining and so forth. The question I had was, to what extent do you think semantic technology is suitable for making meaningful inferences about big data sets?
So the comment was, first of all, Facebook has massive amounts of data, perhaps a petabyte every 3 days. And there's no doubt that Facebook is at the forefront of collecting massive amounts of data. They're actually a customer of ours, although I can't comment a lot on what we're doing with them. But I will say that certainly one of the really powerful things right around these big data technologies is they are maturing and being rolled out in the context of some of these amazingly high scale environments. And so it means that those of us with a mere petabyte of data or 100 terabytes of data can rely on having some great capabilities, and we're not now on the bleeding edge of analyzing and processing the data, that there are those working at 100 times that scale in these systems, and they are at the bleeding edge and doing very creative and complex things in order to work at that scale. So that's the first comment. The second comment or question was around what about the use of semantic technologies to analyze these big data techniques. And honestly, I would say that I think, and we'll talk about a little bit later with data science and big data, that the best thing is to be fairly agnostic on techniques, that there's a large number of techniques that might work, and that it's not a question of taking one technique and saying this is the hammer, the golden hammer that'll drive all the nails. Instead, it's more a question of having a flexible system where you can try a lot of things and empirically determine what works. Right? I'm a big believer in that and saying try a lot of things and be open to new ideas, because there's so many different interesting traditions and capabilities, and I've seen in data science teams people trying a variety of different approaches and ultimately coming up with good results, that you want to be able to use a variety of techniques for a variety of problems. So this diagram here talks a little bit about what we see as a common high-level architecture for how big data systems come together. Now, the first thing that's worth noting here is this is not necessarily a statement of what's the first thing that someone would do when they start working with big data. This is more of a definition of what we've seen at a fairly mature big data architecture, the kinds of patterns and technologies that come together, that you see different systems working with data in different ways, that you have a natural divide on the top with interactive systems, not necessarily transactional, but systems that are acting in real time and engaged in responding quickly to events, versus analytic systems that are being more used to understand what's going on. And then on the left, more real-time, low latency systems, and on the right, higher latency batch systems. Right, so in the bottom right, in the batch analytics world, we see Hadoop as having really firmly established itself as a foundational standard around big data analytics. What Hadoop is of course evolving every month, and will continue to be. So there are certainly some things like highly iterative machine learning algorithms that MapReduce is not ideal for, and there are approximations, but what we see also is the advent of lower latency alternatives that will ultimately be folded into the Hadoop paradigm. so that you'll see things like Yarn with Spark or BSP or MPI implementations on top of it, starting to innovate further. So we believe that Hadoop is going to be a core foundation for batch analytics, including doing analysis of new models, improvements, training machine learned models, scoring models at scale. And one of the things that we think is a very powerful and important tool and technology on that is using R in a scalable way, that R is an open source statistical environment with the rich libraries that kind of meets the cost model of Hadoop. So even when you see some of the traditional statistical vendors out there offering products for Hadoop, we typically see that they can't price it in a way that makes sense to run on Hadoop, right? And that makes sense because they can't give away 90% of their market by making it easy to switch from their expensive legacy environments to Hadoop. So we see a lot of activity in the bottom right around training models, scoring models, and just doing production data processing, taking in these complex data sets and organizing them. And the way that we see people working with these data sets is not the traditional building cubes and dimensional models for an OLAP type analysis. Instead, we see different ways of structuring data incrementally to find new intermediate representations that are more efficient. So a great example of that might be if you had a series of events coming in from a device and you wanted to transform that so you had a wider view of history in a time series that you could access in one place for all of the events on a device at one time keyed by the device, right? That's a way of pivoting and organizing the data, and maybe, by the way, joining in, denormalizing and joining in some relational data along the way to make it easier to work with the data as you want to do analysis on it, right? So there's a lot of that kind of activity going on as well of doing distributed processing of data there. But big data is not just around batch analytics. Right? A lot of times what we see is it's important to be able to feed it in for real-time systems, whether it be real-time analytics. That's becoming interesting, right? That traditionally, the way you would do low latency queries on these kind of data sets is you would crunch it down ultimately into an environment where you could then push it into a relational MPP database and do queries on it. We're starting to see the emergence of technologies like Impala and Hawk and Drill and so forth as low latency query engines that let you formulate queries in a schema on read way on data that's sitting in a raw form in Hadoop with quick response. And indeed, Hive is a common engine for querying Hadoop is speeding up that there's active work on the Stinger and Tez projects to make that run faster. And there are some questions, yeah. I mean, I think so D3 is a JavaScript library for visualization. You know, I definitely see D3 as being used for visualization. I think there's a whole range of visualization techniques, right? So D3 I see as being very useful if you want to build very packaged visualization, like in that slide I showed you where you want to come up with something very finished for a less technical user to just sort of show them what's going on, right? And in the middle ground, you see visualization tools like a Tableau, a Karmosphere, a Datamir that have more packaged visualizations that a user who can use a user interface can drill through and get more rich insight into the data. And then kind of the deepest visualization will be workbenches like an RStudio where you can, or Revolution R, where you can really dive in and use mathematical functions to plot data and to really tear it apart and get deep insights into it, right? So you have this whole range of requirements around visualization, much of which is, again, on that bottom left of real-time analytics. Yeah.
Nathan Mars talked about the Lambda architecture in his big data book,
Mm-hmm.
and I was wondering how that relates to the reference architecture.
Sure. So you know, there's a number of elements of the Lambda architecture that I think are very consistent with this reference architecture. I mean, the basic flow of wanting to have your interactive systems be able to have low latency data sets that they look up to respond to events and stream data back into a batch an analytic world where you can update batch computed views and then push them back up into the real-time system, right? Nathan's notion of having a difference between a query database that's really a read-only view of data versus a read-write database. Now, in practice, we don't see a lot of people separating these. We see a lot more commonality of putting both of these things in one NoSQL database. So while that's an element, but at that level, the patterns are very consistent. There are some elements of what Nathan views in terms of how to represent data in the Lambda architecture that I think are something of an idealist software engineer view that everything is organized perfectly. And we see a need to design big data architectures to deal with systems that are not so tightly controlled, right? I mean, it's like the way the web works is a great example of how no one would ever design the web if you could control all the pieces to have malformed HTML and badly behaving servers and systems along the way. And yet, by having a system that is so loosely coupled and tolerant of noisy data and imperfection, you've got a much more robust system than something that's perfectly engineered, right? So I think that, if anything, my view is that the Lambda architecture is sort of based on an assumption that you've got somebody designing the whole system in a perfect way and then having a clean way of organizing the data, but that in practice, things are often more messy. You don't have such full control. But the idea of having immutability, of keeping all the data, of having not trying to maintain an ongoing read-write state of something complex that you can reconcile conflicts through batch computed views are all powerful ideas that are certainly very consistent with this view. Yes?
So let's say there's a worst case scenario, or not necessarily worst case scenario, or in some respects it could be best case scenario, where you have your Intel, and every 5 seconds you take a CPU utilization value from every CPU you have in field, send it off to some data store. At what, in that scenario, or in some derivative of that scenario, how much use are you going to get from very largely like historical data? Say we're in 2013. What about year 2000? Are we going to get any value out of that? Should we throw that into a storage that you don't necessarily have immediate access to? What's your thought on that kind of?
Sure.
Is that part of the infrastructure at all?
Yeah. I mean, I think Intel is a great example, of course, of somebody that supplies a component and they have a disconnected component that they have no feasible way and probably a lot of difficulty in getting the packager of that component to give them data back, right? But as a thought experiment, there definitely are data streams that can be so massive that it's difficult to, even with modern networks, to collect, right? I mean, we've seen that. I mean, we've talked with people who are mobile carriers where it costs dollars to move megabytes of data, and they're saying there's no way we're going to in those applications capture a petabyte of data with it being $10 a megabyte. We're going to have to analyze samples and have more distributed intelligence, right? So, the future is arriving unevenly. Some applications, the data, the networking costs are too high to move all the data, and it will force you into a space of having smaller samples you analyze and push intelligence out to be decentralized. That's not common in my view. There's very few people that have that scale of data that have that kind of problem, so it's an exception. It's certainly, I have to acknowledge, I've seen customers that had that as a constraint of theirs that they really didn't, but a lot of times I've also seen that people assume themselves into that problem prematurely, that they believe that they've got way more data than it makes sense to move, and you can challenge that assumption and say, well, let's really work through the economics and see how much data do you have and what would it cost. A petabyte of data in today's architectures costs, it costs money, but at a few $100s per terabyte per year, it's not crazy to think about storing and processing petabytes of data. In fact, many of our customers do, right? So in an old world where it was tens of thousands of dollars per terabyte per year, it was crazy to talk about storing and processing petabytes of data, right? And Facebook couldn't possibly process their data on a system like that, right?
How often do you find that the data itself is either bad data or meaningless or useless, and you can't do data cleansing, obviously. So So how do you filter through the noise? How significant a problem is that for your customers?
So how do you deal with noisy data? Well, I think one of the things that is powerful about a big data approach is by putting data in a raw format and following principles like immutability instead of destroying the old data and having summarized processes where you now can't recover, you have the maximum ability to deal with such problems, right? What causes bad data? Probably the number one thing is software bugs, right? Something that was computed wrong, right? So you might be able to undo a software bug. You might be able to analyze and limit the scope of that damage. You might be able to do a variety of things when you discover some of those issues. The other thing that, in fact, one of the most common sources of bad data in my experience has been external feeds and someone else's software bugs, right? And certainly having good systems for being able to limit. Often it's going to be as simple as saying, well, we've got our processing systems well organized so we can roll back and recover based on a fixed feed where we recover. But ultimately, the best you can do is have the raw data and be able to do downstream transformations and reprocess to the best of your ability. So there's power in these techniques because you had both the ability to store the raw data and enough processing capacity to go back and reanalyze things, right? Again, the classic data warehousing paradigm was, I can barely keep up with the stream of data as it's coming in. I could never recompute anything. I didn't have anywhere to store it, and there was no way I had the capacity to rerun anything, right? Well, big data says you should have enough capacity to store all the data, and you should have enough compute capacity to do what-if analysis and try new scenarios and recompute things. And let me not make light of that. At Quantcast, we did multiple times improve our models for measuring the internet. And going back over a petabyte of data and reanalyzing traffic, it was not a trivial thing, right? This was, even on thousands of machines, it was a significant job to go back and recompute history. But it could be done in a way that could never have been done in older technologies. So, segueing in and being respectful of people's time, just to wrap up, going for some of the technology, one of the things I think is really important about big data is also the notion of having an agile methodology, right? That you want to have an approach of getting value out quickly, having short cycles of testing and learning and experimenting. The book's not been written, right? That what you can do with big data and data science is still very much wet paint. What's exciting is there's lots of things to try, lots of ideas. Many of them won't work, but the way we find out what's going to work is by experimenting and testing things and having close alignment between the business and technology with discrete projects and showing value, right? Not having a project to say, well, let's take 2 years and implement something. Instead, what can we get done in a few weeks and start to show the business this stuff works and open up more vistas so that we can show more value. Once you've landed kind of a foundational use case where you've created value, that can open up a whole portfolio where you might have some low-hanging fruit of just doing insights in one afternoon and being able to show something interesting to the business. It's hard to justify investing hundreds of thousands of dollars in a whole system to come up with the insights of one afternoon. But once you have it, you can do that and create a lot more value, as well as bigger, more ambitious projects that aren't low-hanging fruit. And to me, most often the low-hanging fruit in big data is around what kinds of things do I want to solve for, understand that it's clear that we've got all this data and we haven't been using, right? So in the Internet of Things, it would be data from our products. In consumer-facing applications, it might be our web logs and advertising traffic. What are the things that they're just crying out that we're ignoring? And if we just use it, we should be able to move the needle on something we're already doing on our business, get insight and operate in a smarter way. And that kind of low-hanging fruit is usually the first thing that makes a lot of sense to start moving on. And just thinking about, well, what does that mean practically inside this process? What are some of the roles and skills? And in our view, big data teams have kind of at their core data engineers and data scientists. And they're complementary, but they're both important and in different ways, right? So fundamentally, data engineers write production software. So it's less of a new role, right? Production software engineering has certainly been around for a long time, but in a big data context, it has some interesting characteristics, right? You do typically see a need to make data more accessible, but also what we see is that people that have been very specialized around a narrower set of tools, a specific language, are not nearly as successful in doing big data as polyglot programmers that know a variety of techniques that like to dig into data and look at what's going on under the covers and not just implement something and it's done, right? That like working with the business and like putting together a variety of tools, right? So that from the engineering side, those are some of the characteristics. We see that some of the interesting problems that data engineers run into in big data systems are ingesting large amounts of data from a variety of data sources and modeling data in a NoSQL environment where we all have, those of us who have programming backgrounds and data modeling backgrounds have long learned kind of how do you work with data in a relational model. But a lot of what's going on in big data is saying the world's a little more complex in the relational, and how do we model things with more complex structures effectively? Tying in the programming needs with the business, right? So what are the questions the business really wants to ask of their data? How do you make the data accessible, right? How can you drive to faster cycles of testing and learning with a agile methodology where you produce quality along the way, but you don't overinvest. You allow for getting data out and testing it out, right? Where you're working and of course, like in any emerging technology space, it's fun, but it's also, it's not as fun when you're debugging relatively new and unproven technologies, but it's part of the job, right? That big data is exciting, it's new, but it's complex. There's a lot of configuration. A lot of the systems, notably Hadoop, have been built very much with the notion of everything's possible, but you may have to dig through some source code to figure out how to configure it to work, right? So there's certainly those are some elements of data engineering. And then from a data science standpoint, ultimately we think the big goal of data science in this world is delivering knowledge to the business, that there's a need to do both exploratory analysis, understanding what's going on, digging into data, getting a feel, seeing the trends, visualizing to the question earlier, and then confirming, really testing hypotheses, being rigorous and proving things out so you can make solid decisions and perhaps even automate those decisions in the form of code. Data science to us is also very much something that requires you to blend math, science, and programming. That we really don't see that it makes sense to have a separation where you have a statistician working in a math world and having a programmer who does all the work on the data. That understanding the data and digging into it really requires programming skills. It doesn't necessarily mean that data scientists should be focusing their time on writing production software, but it does mean they need to be able to write some code and dig in and analyze the data. And there's a question.
More in terms of the data engineering or data infrastructure, what's your take on Hadoop sitting side by side with other NoSQL databases like Mongo, which is more document-based, or key value systems like Cassandra or Oracle? I mean, is that redundant? Can Hadoop solve most problems on its own, or what's the direction you see going forward? A lot of shops, I think, are hybrid, right?
Yep. So, and I think different tools serve different purposes, right? That there's clearly ongoing debate as everyone tries to make their platforms more valuable and solve more problems, right? But we definitely see that NoSQL databases for serving users, scale out, real-time serving, like a Cassandra, a Mongo, have a place. And we don't see a lot of people applying even HBase, which is more of a NoSQL database built on the Hadoop stack in those kinds of edge-serving interactive applications, right? We do see HBase being very useful for fast analytic access to data, where its deep integration with Hadoop and fitting in with that environment can be powerful. And the other side that we often see is low latency access to data is not just around key value lookups or range scans, but often having smart indexing, which is very much what a search index can do. So technologies based on Lucene, like Elasticsearch or Solr or Splunk, become very interesting as well. Right? So we definitely see that having different systems coming together is important. And indeed, a lot of times we see companies starting to say that they want to have scalable real-time processing. So technologies like Kafka as a scalable message queuing system that's open source, or Storm as a scalable way of distributing computation are becoming interesting. They tend to become interesting when you're a little bit more sophisticated. So we see most organizations starting with focusing on batch MapReduce analysis, and once they get to a greater degree of sophistication and maturity, then they start to do interesting things with more complex real-time analysis scenarios. But you can go a long way with a NoSQL database and an app server without having to go to the complexity of scaling your computation across something like Storm in many cases. So just to wrap up the discussion around some of the different roles, so we see that the data science role, which is around this combination of understanding the business, analyzing the data, being able to really work with that data, do some programming to be able to support these core functions, right? Knowing what questions to ask, having clear analysis, being able to do the various forms of analysis, and of course it's an iterative process, right? As you learn things, going back and trying new models and keeping close track of what you have done, right? One of the things you always want to make sure of, if you have a negative result, you're really clear on what you did. So somebody will inevitably want to come back and reanalyze what did you do and maybe try a different approach. So it's important to know what was actually done and not have an anecdotal, vague notion of, well, this thing failed. Well, what exactly, right? Maybe there's a new way of doing this that's going to be valuable. So that's what I had in terms of prepared comments on Internet of Things and big data and data science. I guess I'd be remiss if I didn't say that at Think Big we're hiring, so certainly would welcome those who are interested in opportunities to do some of the data engineering and data science work, and certainly would love to hear if there's any further questions. Yes?
So, yeah, I think generally from like a little bit of statistical perspective where we first model the data using either a hidden markup model or a Gaussian mixture model or something like that. What I'm seeing, like, where is the feedback loop? So let's say the statistician goes in and says that he's modeling that particular data set in that format. How is it propagating to those higher layers of querying? I don't see any loops in that architecture that's coming to R or going back. So, in your experience, how do you? Is it like, okay, this month we are going to try, the hidden markup model. Next month we are going to try. I mean, how do you go about doing that?
Sure. So what we see typically happening in the data science cycle is you'll have data coming in from a real world system, and you will have the ability to do a lot of simulation, testing, analysis of what's possible. And depending on the problem domain, that might be a lot or it might be a little. And then out of that, creating a model that you can then push out, typically doing this export, so the predictive analytics gets scored, and you now have a model where you've got the ability to respond in real time. And in many cases, you'll also see blending deep propensity modeling in batch with coefficients that get applied in real time as events are coming in, right? That there's a lot of systems where the batch computed view of a lot of history is part of the model, and so is what happened in the last 5 minutes is super important, and I want to apply that too. So I know how to at least approximate that scoring function in real time, right? So that's a general flow where you apply those models, typically in a champion challenger mode where you're going to have multiple A/B tested models that are running, so that you have your current best champion and you've got a new model you want to try out as a challenger. Right, and you need to tag it. You need to know exactly what was running, so you know how you scored things and what happened, so you can really analyze what happened. Right, you run it, and then you feed the data back into this environment, so you can analyze and say what's working. Right, how is my new model performing? So yeah, absolutely. What we see is typically it's a blend. You do a lot of scoring in batch, but you need to have some amount of real-time scoring in many of these systems. And not always is the real-time scoring perfect. It might be a decent approximation based on your trade-off of how accurately you can score and how important it is to score. Right, so that's a common scenario that we see. Now there are other systems where people accept batch scoring, right? Like classic search indexing is done that way, or if you look at like how LinkedIn does people you may know, that's a batch scored algorithm. It's basically an n-squared problem, right? Comparing all people to other people minus one and saying how likely are they to know each other. But you don't want to do that in real time, so you compute it in batch with heuristics and you feed it out, load it into scale-out query database, and they don't, as far as I know, do anything in real time. If you just connected with somebody, they don't update that model. The next night, they'll come up with a new set of people you may know. Yeah.
Does this reference architecture differ from data virtualization?
Well, I think, how does this reference architecture differ from data virtualization? Well, I think it's very different in the sense that there's a lot more materialization of data in this architecture, right? That you've got a series, you tend to have data pipelines that are transforming data and creating derived downstream results, denormalized, joined, cleansed, that you can then build on, right? Rather than trying to say, pull it all together on the fly, right? So that in fact, there's a lot of limits on what you can reasonably do with data in a single format in one place, trying to pull it together and analyze, right? So often it's, and a lot of it is too, is batch analytics with something like Hadoop are very much, a lot of the power of that is being able to do sequential processing, right? Under the covers, spinning disks are a much higher throughput when you access things sequentially. So being able to organize data in that way is a lot more powerful than a random access index lookup, which I think most of data virtualization technologies would rely on indexes to pull data and combine it on the fly. So time check, how are we doing on time?
We're good.
We're good? Okay.
How do you actually know, I mean, this day, I mean, okay, so 10 years ago and I've done this, okay, so that's why I'm checking you on this. How do you know it's actually sequentially on the disk?
So it's not
Because
perfect.
nowadays
Yep.
it's different from 10 years back where you actually know it's actually sequentially on the disk.
Yeah, well, yeah, so one of the things certainly is it's access to data. As you get fragmented disks, right, as you start to have fragmented disks, you definitely can have more seeks than you would expect or you would like. And so part of running a system effectively is to make sure that you don't overfill your disks. I mean, there's a lot that goes on under the covers.
I absolutely agree. So I'm on the same page with you. We're trying to get this the low latency. How do you ensure that low latency? How do you know that it's not just a block storage somewhere?
Well, I mean, so typically the way people implement Hadoop, for example, is that they have direct attached storage, and so the sequential writes on systems that are not fragmented will therefore translate into sequential reads, right? So that's a typical pattern. It's not a question of it being absolutely always the case, right? There will be cases where you might have fragmentation and you might get a single block written with multiple seeks required. But statistically, if you're administering the system effectively, you're going to get a low number of seeks per read.
So this is slightly off the wall question maybe, but have you had people, companies approach you where they want to have big data in the back end and some sort of wearable technology devices like Google Glass? Do you see that as a viable use case?
Absolutely, yeah. We're dealing with, one of our customers is a very well-known brand that has wearable consumer technology, and they're very interested in the ability to apply these big data techniques both in batch and in real time to support those.
Can you sort of visualize, so to speak, a scenario where you've got something like Google Glass? What would you look at? What kind of data would you have in the back end that would be meaningful for somebody working on this?
While I don't have any insight into what Google is doing to support Google Glass today, I would believe that they're probably using big data techniques already in terms of being able to integrate a complex view of what's going on in the real world and you know, your geolocation, your information, in order to have a relevant experience, right? So I think those kind of personal analytics applications are great examples of where big data is powerful. And I think, you know, Google Glass is a prominent kind of a first meaningful commercial foray into wearable technology of that kind that's fairly general purpose. I think that it's going to be very interesting over the next few years. Whether Google Glass in its current form becomes successful, I think it's the opening round in really a serious effort to commercialize wearables. So it's exciting. And I can't imagine it working without big data. Yeah, I would think so. Although I don't want to speculate too much on wearables, but I do think they fit very squarely into the Internet of Things, and the analytics around them, the feedback of that data and blending complex data sets together to support them is certainly going to be important. Yes.
So going along with a crazy question, what do you think the viability of having big data as a service for consumers? So essentially, once we get to the Internet of Things, and to the point where my body's being tracked, like I'd like to see some real-time visualization of my heart or something like that. You see people doing it themselves, but like do you actually see a analytics platform being monetized to consumers eventually throughout the life cycle of this space?
I think what you're going to see is a continuation of commercialization of big data behind the scenes for consumer-facing services, right? That large amounts of consumer activities, like when you go into Facebook, when you start to interact with Google, I mean, there's a whole range of applications that people will, lots of mobile applications. Consumers are having services powered by big data, and I think over time they will get more sophisticated and powerful, right? So, I guess I don't think that consumers are going to turn into data scientists and do a lot of deep analysis on their own data. There will be exceptions, maybe some of them in the room, who will want to get a hold of their own data and do data mining techniques on it. But I think most consumers will rely on services that use big data behind the scenes to create packaged value for them. So I think it's a little different than in the business realm, where businesses can and must invest in data science to tailor the results to their specific needs. Yeah.
Well, I'm trying to launch a platform or organization that would be owned and managed essentially as a co-op, a fraternal benefit association, by the members, so that they could anonymously share, manage, mine, market, monitor their data as they chose for their benefit, using all these resources, basically their suppliers, their service providers, but they would have the original and final control of their data and how it was managed and sold for their benefit.
Excellent. Well, I think there's definitely a lot of interesting questions around control of data and access to data, and at the same time, a lot of value in being able to share data in safe ways. You see a lot of challenges as people look to develop products or offerings in terms of, well, can we get access to data in order to do it? Yeah, question in the back.
Would you comment on what you observed in terms of what the sources of machine data, whether they are sensor directly captured data, or whether they are machine generated in terms of the server logs and all the rest of it, and what the trends are, and also some part of the sensors, the implementation cost could be pretty high. What might be some of the challenges and things you've seen?
Sure. I think there's a big range. There's a lot of variability depending on the kind of device and the kind of system you're talking about, right? I mean, one of the first things is Internet of Things can range from small disposable devices that need to have incredibly cheap sensors and incredibly efficient ways of capturing and working with data, up to super high value industrial equipment that costs millions of dollars, right? I'll say that I think that complex high value items are moving faster because the cost of collecting the data, of sensing things, of analyzing the data is small compared to the value of those things, right? So I think in general, the mega trend is you're seeing more activity around big, expensive, complex things, and over time it gets driven down to cheaper, more broadly deployed things. And which is interesting because I think a lot of times the intuition and the consumer press looks at it the other way and talks about lots of little cheap things, but unsurprisingly, it's a lot easier to start with expensive, high-value things, right? So that's one. There's depending on the domain, there's domains where it's largely around direct sensors, right? Measuring voltage in smart meter is a great example. Measuring flow in a manufacturing system, measuring temperature, right? These are pretty direct sensor measurements. Other times, it can be pretty virtual measurements like capacity usage or rate of transaction processing, right? Those are sensor readings, but they're virtual. They're not measuring anything physical in the real world, right? And likewise, though, I do think that certainly in increasing amounts of these things in the Internet of Things, there is software with logs, and there's usually a lot of insight in that data, the data in those logs. Yeah.
Just to bring it back to our host here, how long do you think it'll be before this type of big data analysis is going to be done by ELAN's professionals?
Well, I guess from the talk we had, from the opening comments, there is some of this being done by ELAN's professionals today, right? That the overall context is there's a whole new set of skills and new capabilities required And there's a range of approaches, right? People, there's a lot of interest in companies hiring. There's certainly a lot of independent contract work. Companies like ours provide specialized teams with a methodology and integrated skills. And you see the whole market is moving towards demand for big data and data science skills.
When does it transition from, say, projects that are hundreds of thousands of dollars to projects that are tens of thousands of dollars? When does that occur? Or does that occur? Or is there a critical mass that needs to be involved before you can consider this?
Yeah. I mean, I guess certainly in any big project, you'll have smaller projects, right? So you can break things down. But I think maybe behind that question is the fact that today big data still takes a fair bit of engineering, a fair bit of assembly, a fair bit of analysis. So it's still being applied to fairly high value problems, and it's not something where you would typically say, oh, just come in here and knock off a few $100s of for a day of analysis of the data. Although you definitely see trends where a lot of startups are using cloud services like Amazon Web Services, and they can spin up a cluster and analyze data for an afternoon. So there are cases where you could today see, I just need a little bit of help analyzing one data set and post that up on an ELANS type system to get some help. Yeah.
What are the top 2 or 3 verticals for your company, and what do you see as the emerging verticals in the next few years?
Okay, so the question is, what are our top verticals and what do we see as the emerging verticals in the next few years? I think that one thing that's been interesting is that big data has been one of the first technologies where the first mover was something other than financial services, one of the first major broad-based technologies, right, where online advertising services have been the first movers. For us, tech companies more broadly defined, high-tech manufacturing as well as online, have been the most important vertical, with a close follow-on from financial services. Banks, brokerages, investment houses, right, that they tend to be the other large vertical for us. But we're seeing work in other verticals like retail, like telecommunications, like life sciences. I think that the industrial internet, the Internet of Things, will expand, and that will become increasingly important. That it's being led by tech companies, but that many of the same patterns and techniques apply. The technology is becoming important to all kinds of products, and therefore that will be a follower. Right? Whether there's medical devices, whether it's supply chain manufacturing, energy, oil wells and oil and pipelines, et cetera. So that will be a follower, as life sciences too. Right? I think the use of things like gene sequencing that's improving even faster than computers is going to generate unbelievable amounts of data, and you're going to see the absolute requirement for oncology labs, for example, to routinely process petabytes of sequenced data in order to treat patients. Right, that's going to be a follower. It's moving pretty quickly, so it's another area. Right? And one thing that's interesting is speculating on this is it's hard because there's so many interesting areas where big data can apply that there's a lot of horses in the race as to where it's going to move fastest. Yeah.
Have you seen an increase in instrumentation on the type of high-value products that would typically fall into the MRO area, manufacturing overhaul scenarios?
I mean, I'd say that we haven't seen maybe a lot of change in instrumentation yet, but I think the feedback loop will be there, that as you start to see changes in being able to analyze and work with that data, it's going to drive some interesting revitalization in a space that probably has had not a lot of innovation, right? So you really do see that once you start to use data, it changes your notion of what data you want to capture and how to work with it, right? So I think there's going to be a lot of changes throughout the supply chain. Yeah.
Just like from a large concern, isn't Caterpillar kind of a leading edge with their data collection on their big equipment and building on a power-on-hour type of model, and setting up their own networks because they're in isolated locations?
So I've just read a little bit about Caterpillar. I'm not deeply familiar with what they're doing. I know that they've been innovating in this space, so I'll take your word for it. And I think it's certainly a good sign, right? I mean, we've seen GE is also talking about doing things with connecting their industrial equipment. So it's great to see some of the big manufacturers of high-value equipment investing and seeing value in these techniques. And I think whether it's Caterpillar or jet airplane engines, you can see definitely that notion of these complex, high-value equipment. There's so much value in being able to analyze and do smarter things with that data that it's moving fast in those places. Yeah.
You mentioned access to data. What are some of the other challenges in the big data space?
So other challenges in the big data space, I mean, we alluded to it in talking about the skills gap, right? That there's not nearly enough people that know how to do data science and work with these systems. Other challenges we see is a lot of times companies are still trying to apply the old playbook to the new world, right? So they're trying to do things like it's a data warehouse, and they're trying to use kind of the approaches to implementing packaged enterprise applications that don't really fit to assembling solutions and doing analysis in more complex data sets, right? So we think all of those, as well as the usual thing around any emerging technology of people just trying to figure out what goes where and what pieces kind of fit together. I mean, this is not a simple diagram, and understanding what pieces you want to use and how. We see a lot of customers that are, misunderstand what works well and what does what, and so all of those are things that we see companies being challenged by. And then the last thing is sort of appreciating what are the high value applications, what kinds of things are working, so be able to say these are good use cases to apply these technologies.
Two questions. One, I think you just alluded to, warehouses and data marts. Will they continue to have a future in this world? And the other one was in regards to relational databases and mission critical systems. Are those going away? Are they here to stay? In terms of package solution?
Sure. So great questions. I'm glad you asked. So the first thing is we see people bringing in big data technologies as complementary to their existing systems, right? So we're not seeing people shutting down their data warehouses and unplugging their OLTP databases. We see people using big data to complement them. So I think there's a viable future where instead of the classic data warehouse view, you've got a data lake in Hadoop that's feeding a bunch of data marts that are organized for specific analysis. But the data warehouse that you invested $5 million in 5 years in isn't just going to be unplugged. It'll continue to live in an enterprise that has one. But I do think you're going to see the focus of energy of new value creation shifting, right? So you're going to see that traditional warehousing and data marts are going to be less of an area that people continue to invest in, and more of an established asset, and more innovation is going on and new problems are being solved around these new platforms. And in a similar way, while I don't see kind of core transaction processing moving off of relational databases, I think a lot of the activity around real-time interactions is around systems of engagement, where you have these complex NoSQL databases that are applying machine-learned models that are driving rich interactions. But those are systems where there's a big difference. Like if you're interacting with your bank and the bank screws up your transaction, that's not acceptable, right? But if you're interacting with your bank and they don't recommend the ideal thing for you, you can probably live with that, right? So there's a big difference in the importance of how critical this stuff is to have things done perfectly. So there's interesting critique, you can say of, while one bank's system is ACID transactions, and when you start looking at the banking system as a whole, it's also an eventual consistency system with all kinds of problems, right? Because people pass checks from one bank to another, and there's no two-phase commit. Anyway, that's another discussion. All right, yeah.
So one question I had is the demand, for example, amongst your client base, is typically coming from those who already are working with data and who just want to do more, or is it typically more coming from business people who are saying, I know that big data should be able to give me better insights, and I should definitely be able to make better decisions, but I don't have the ability right now?
I mean, I'd say that most of our customers certainly have some kind of analytics access to data, doing something with it, but there's often a pent-up demand and a recognition that there's a lot more that could be done. Maybe some data sets aren't being analyzed, or some big problems that aren't being addressed effectively. All right.
Last question.
Okay, one more question.
Sort of in regard to relational databases, I worked at AT&T in the 1990s, and it was like, kind of look at it as maybe the first killer app in the cloud back in the 1990s. We had about 80% market share at the time of business and consumer, and analyzed really huge data sets. But the technologies then were mainframes and SaaS. And we're an analytic group. One of the things that we discovered, this is really sort of just when relational databases were coming in, that SaaS was very unproductive for just exploring the data to see what was there. We spend tons of time using the SaaS data step, if you're familiar with SaaS. But it's pretty inefficient, and finally get to the data set we want, and we run our regression analysis on it or other statistical programs on it. And one of the things that we discovered is that relational databases could actually do two things: boost the productivity of, once we found the data we're interested in, pulling it together in flexible ways and feeding it into SaaS. But also the whole process of normalizing the data, getting it into third or fifth normal form, was analysis in itself, because it helped us see what were entities and the relationship between entities. And we definitely didn't rely on the IT group to do it, because that would have been very, very slow. But we developed those skills ourselves, because it really helped, just dramatically boosted our productivity. Do you see relational databases continuing on in that role in big data, or are there other tools? Can Hive do that in the big data world?
Yeah, so I think that there's the further extension of having more flexibility into how you work with the data. There's never a substitute for understanding your data and digging into it if you're trying to solve a problem, right? And I think what you were saying in terms of the process of looking at the data and figuring out how to normalize it was very productive for you before trying to do modeling on it, right? So that continues to be true. I think, though, that especially as you get into more complex, less structured data sets, that having tools that let you work with a variety of techniques, sometimes Hive, which gives you a SQL interface, can be powerful. The ability to drop into a user-defined function where you've got more complex data. Sometimes it might be a data flow language like Pig. Sometimes it might be a more general purpose programming language like Python or Java to work with the data. So, I think having a variety of tools for how you work with the data and analyze it is important. Being able to start your analyses small and scale them up is important, right? Just because you have the ability to work with massive amounts of data doesn't mean that the first thing you should do is throw your first idea at a massive amount of data. A lot of ideas can be tested at small scale and refined and incrementally work your way up, right? That you learn something at each order of magnitude of volume, right? So that's a common best practice, is to analyze things at increasing scale and kind of turn loose the most complete analysis once you're pretty confident that you know what you're looking for. So it's certainly, I think it's an ongoing evolution in how people analyze data, and I think having capacity to do a lot more is fantastic, and flexibility in tools is fantastic, but there's always an art and a skill in the practitioner that can't be ignored. All right, well, thank you everyone for attending today. It was a pleasure talking to you.